Let's look now at our second type of improper integral, where our function has a discontinuity, and of course the most interesting one is where the function goes to infinity. Now, this works a little more generally, but let's assume in this case that our function is continuous on the interval from a to b, and it's discontinuous at b. And again, the most interesting case is where it goes to infinity at b, because we can use our previous techniques to integrate with a jump discontinuity at b. Well, then the integral from a to b of f of x dx is the limit as t approaches b from the left of the integral from a to t of f of x dx, if that limit exists and is finite. And of course, if it doesn't, we're going to call this integral divergent. If f is continuous on the interval from a to b, where that's an open interval at a, and it's discontinuous at a, then the integral from a to b of f of x dx is defined as the limit as t approaches a from the right of the integral from t to b of f of x dx, if that limit exists and is finite, and otherwise we say this integral is divergent. So one of these improper integrals is called convergent if the corresponding limit exists, and divergent if the limit doesn't exist, as we had before. If f has a discontinuity somewhere in the middle of a closed interval from a to b and is otherwise continuous, and if both of the integrals from a to c of f of x and c to b of f of x, as defined above, are convergent, then we say that the integral from a to b of f of x dx is convergent and equals the sum of the integrals from a to c and the integral from c to b. Otherwise, we say that this integral from a to b of f of x dx is divergent. So if one of those integrals from a to c or c to b diverges, then the whole thing is divergent. Let's try to apply our new definition. Suppose I want to determine whether the following improper integral converges or diverges. The integral from 0 to 2 of 1 over x minus 2. And of course the problem here is at 2, the limit as x approaches 2 of f of x is infinity, so it has an infinite discontinuity there, and otherwise this function is continuous on this interval. Well, we can apply our definition. The integral from 0 to 2 of 1 over x minus 2 dx is by definition the limit as t approaches 2 from the left of the integral from 0 to t of 1 over x minus 2 dx. And that integral from 0 to t of 1 over x minus 2 dx is well defined as long as t is less than 2, because the function is continuous on the closed interval from 0 to t. And we can actually find an antiderivative pretty easily for this function and apply our fundamental theorem of calculus. This is the limit as t approaches 2 from the left of the natural log of the absolute value of x minus 2 evaluated at the endpoints of integration, which are 0 and t. So it's the limit as t approaches 2 from the left of the natural log of the absolute value of t minus 2 minus the natural log of the absolute value of minus 2, which doesn't exist because as t approaches 2 from the left, t minus 2 approaches 0, and therefore its absolute value approaches 0, and the natural log of the absolute value of t minus 2 approaches negative infinity. So this integral diverges.